In ordinary eager PyTorch, loss.backward doesn't move a single weight. The moment backward returned, w.grad held -8 and b.grad held -4. Neither w nor b had moved. Backward writes a gradient into each leaf that requires 1. The optimizer changes the weights later, and only when I call it. That's the gap where forgetting 0 grad quietly changes your training instead of failing loudly. The prediction is w times x plus b, so 3 times 2 plus -1 is 5. The loss is the quantity, prediction minus target, squared. 5 minus 7 is -2, and that squared is 4. In grad mode, PyTorch records an operation when at least one input requires gradients. It hangs a backward function on the result. The loss came back with grad fn of PowBackward0 and the prediction with AddBackward0. That's the structure, and I never wrote a line of it. PyTorch does not read my Python source and differentiate it symbolically. The PyTorch Autograd notes are explicit. In eager mode, PyTorch records the tensor operations that actually execute. Put the calculation inside an if statement, and the graph holds only the branch that ran. The next forward pass builds a new one. W and B are different. I created them directly, so they are leaves. They require gradients, and no recorded operation produced them. That's where PyTorch keeps the answer by default. The loss is one scalar, so backward starts from an implicit seed of 1. That is a property of scalar outputs, not a universal rule. Each node combines the arriving gradient with its local derivative. The derivative of the square is 2 times the quantity, prediction minus target. So 2 times -2 is -4. Through the add, d loss over db is the same -4. Through the multiply, d prediction over dw is x, or 2, so -4 times 2 is -8. My run printed that into w.grad. Backward wrote a number down. It moved nothing. Set the training example aside for one separate calculation. Let z equal x times x plus x with x at 2. That one leaf reaches the result 3 times. Each operand of the multiplication returns 2, and the identity path into the addition returns 1. Where those paths meet at x, Autograd adds the contributions. My run returned x.grad of 5, or 2 plus 2 plus 1. Branches do not overwrite one another, they add. Back on the training example. Only leaves that require gradients get .grad by default. Intermediate gradients are working values and reach a .grad field only when retain grad. PyTorch adds into those leaf buffers. It does not replace them. I built the same graph a second time and ran backward again without clearing. The buffers went from -8 and -4 to -16 and -8. The second graph's root was a different object. That was a rebuilt forward pass, not a second walk through the first one. That addition is deliberate, and it's what makes gradient accumulation across micro batches work. Only now does the optimizer act with plain SGD at a learning rate of 0.05. It read w.grad of -8, subtracted 0.05 times that gradient from 3, and w became 3.4. The same update moved b from -1 to -0.8. Those leaves moved because I called optimizer.step, not because backward ran. The next forward pass predicted 6 for a loss of 1. Then 0 grad resets those buffers to none. This is eager mode. On CPU, infloat 64. On PyTorch 2.13. Torch compile can capture larger regions. Compiled Autograd does not have to reproduce this operation by operation picture. Our run demonstrates the eager mechanism. It does not describe what your compiled backward does. So when somebody says backward trains the model, ask what actually moved. Ask which tensors are leaves. Ask who cleared the buffers. And ask whether this is eager or compiled. In our run, backward wrote -8 and -4 into two leaves and moved nothing. SGD moved W to 3.4 and B to -0.8. The next loss fell to 1. The graph you never wrote did not train anything. It handed the optimizer a number. The real question isn't what backward does to your weights, it's what it writes down and who reads it next.